has said there is an invisible monster on the loose. It's a runaway black hole that has got a mass of about 20 million suns. Black holes are some of the most fascinating and mysterious objects in the known universe. They can distort the fabric of spacetime and have an insatiable appetite for matter, making them a force to be reckoned with. The study of black holes has been ongoing for decades, but it's been extremely hard to get something concrete to work with, well, until now. Scientists have finally revealed the clearest image of a black hole ever seen. Music, join us as we dig deeper into the world of black holes and find out exactly what this image means and how it might just change everything we've ever known about them. But before we get to that, let's take a step back. The discovery of black holes wasn't exactly easy. For centuries, scientists and philosophers have wondered about the nature of the universe and the mysterious forces that help it exist. From the earlier civilizations to the present day, humanity has sought to unlock the secrets of the cosmos, and the discovery of black holes has been a major milestone in that journey. It all started with a bold prediction from a brilliant mind back in 1783. English natural philosopher John Michell theorized that there might be invisible objects in space with intense gravity fields that could be detected through the orbit of a star. In 1916, with the publication of Albert Einstein's general theory of relativity, it followed theory of productivity, which laid the groundwork for the modern understanding of gravity and the structure of spacetime. Einstein's theory suggested that massive objects could warp the fabric of spacetime, causing it to curve and distort around them. This concept was revolutionary, to say the least, challenging the Newtonian view of gravity as a purely attractive force between objects. Einstein's theory had many implications for the behavior of objects in the universe, including the possibility of black holes. Black holes are incredibly massive objects that are thought to form from the collapse of massive stars at the end of their lives. Think of it this way: when a star runs out of fuel, it can no longer generate the actual pressure needed to counteract the force of gravity pulling it inward. If the star is massive enough, its core will simply collapse under the weight of its own gravity, eventually creating a black hole where a star once stood. While all of this sounds sane now, back in the day, no one wanted to entertain the idea of black holes, even though Einstein had already predicted their existence. Black holes remained purely theoretical for several years. Some scientists were skeptical of the idea, while others believed that they were too exotic to exist in the real universe. Fast forward to the 1970s when astronomers Louise Webster, Paul Murden, and Thomas Bolton observed an invisible object orbiting a blue star from 6,000 light-years away. The object, codenamed Cygnus X-1, turned out to be the first black hole ever identified. Cygnus X-1 is a binary star system located in the Cygnus constellation, about 6,000 light-years from Earth. The system consists of a massive blue supergiant star and a compact object that is believed to be a black hole. In the late 1960s, a group of astronomers discovered that the system was emitting X-rays, a highly energetic form of electromagnetic radiation that is typically associated with violent cosmic events like supernova explosions and the acceleration of matter onto black holes. What puzzled the scientists studying Cygnus X-1 was the fact that the X-rays were not emanating from the blue star itself, but rather from a nearby object that was totally invisible to optical telescopes, which means it was basically impossible to get an image of one of these on camera. Scientists thought the black hole could be eating up matter from the blue star's outer layer. When the matter falls towards the black hole, it gets super hot and lets out X-rays that telescopes can detect, so that's what they started looking into instead. The discovery of Cygnus X-1 was a major breakthrough in the search for black holes, providing concrete evidence of their existence and opening up a whole new avenue of research. It also validated Einstein's theory of relativity and demonstrated the power of modern astronomy to probe the deepest mysteries of the universe. While black holes themselves cannot be observed directly, their effects on the surrounding matter can be detected. For example, when a star orbits a black hole, the gravity of the black hole causes the star to move faster and faster as it gets closer, causing a Doppler shift in its light. This shift can be measured and used to calculate the mass of the black hole. Another way that black holes can be detected is through gravitational lensing. When light from a distant object passes close to a black hole, the gravity of the black hole bends the light, causing it to curve around the black hole. This effect can create a distorted image of the object, which can be observed and used to confirm the presence of a black hole. Despite the wealth of information that we have already gleaned about black holes, there is still so much that we don't know. What's even crazier is that they are not just lurking in the shadows of the universe, they are everywhere. In fact, there are potentially as many as 400 million of them in our own Milky Way, and at least 2 trillion galaxies in the observable universe have supermassive black holes at their center. They've always been around and they've been everywhere, we just hadn't seen them. Black holes are like the bullies of the universe, they suck everything in and never let it go. That's why it is so important to learn more about black holes. Anything that dares to venture too close will be swallowed up and compressed down to a single particle, essentially becoming nothing. But what's really terrifying is that each black hole is unique, with its own gravitational pull and set of rules, so one black hole could function exactly like another. There are 3 layers to a black hole. The first is the outer and inner event horizon, and then there's the singularity. The event horizon is the point you can never come back from, it's the boundary around the mouth of the black hole. If something makes it past the event horizon, it's pretty much game over. It's like being caught in quicksand, the harder you struggle, the deeper you sink. But in this case, the black hole's gravity is the quicksand, and there's no escaping it. If you do, by some miracle, manage to make it past the event horizon, you'll be sucked further into the black hole to the inner layer. The laws of physics as we know them don't apply inside a black hole, it's like a whole different universe in there. Gravity is so strong that it warps space and time, and everything is compressed down to an infinitesimal point, the singularity. The singularity is the heart of the black hole, where most of its mass is concentrated. It's a point of infinite density and 0 volume, but don't let all of this fool you. The gravitational pull of the singularity is so strong that even light can't escape it. That's why black holes are called black, because they don't emit any light, so they turn everything they come in contact with into absolute nothingness. Despite their terrifying reputation, black holes are also fascinating. So how do scientists even study these cosmic beasts? Well, they study the radiation that black holes emit, along with the dust and gas that surrounds them. It's kind of like studying a blurry photograph of a distant object. You can only get so close before your camera is sucked into oblivion, which you obviously don't want. So how do scientists make sense of all this? They have theories, of course, lots of them. Scientists have been asking the question of what lies beyond the event horizon, and the answer might be mind-bending, to say the least. Instead of just nothingness, what if there's a gate there, a gateway to another universe, another galaxy, or even another dimension? Now we're not talking about just any old gate here, we're talking about something that would allow us to travel faster than the speed of light, which is currently thought to be impossible. But if we could somehow create the technology to do that, we could potentially journey through a black hole and emerge on the other side in a whole new world. It might sound crazy, but it's not as impossible as it once seemed. Some theories suggest that the singularity at the heart of a black hole might actually be a wormhole to another galaxy. Imagine the possibilities. We could travel to distant stars and explore new worlds, all thanks to the glitch in the matrix that is a black hole. Of course, we're a long way from making that a reality. We still have a lot to learn about black holes and the nature of space and time. But the fact that we're even considering the idea of using black holes as a shortcut to interstellar travel is mind-blowing, and if this theory is correct, it could potentially change the world of space travel entirely. But not all scientists think this is possible. Some think that the answer is far simpler, yet no less mind-bending. What if black holes were simply holograms? Enrico Rinaldi, a scientist based in Tokyo, believes just that. His theory of holographic duality posits that to truly understand a black hole, we must treat it like a hologram. That means that instead of looking at what's going on inside the singularity, we should be examining what's happening on the outside. But how can a black hole be a hologram? Well, it all comes down to particles and gravity. According to Rinaldi and his team, black holes operate in the third dimension, and everything that surrounds them is part of the equation. The dust particles and gases that swirl around a black hole actually provide clues to its behavior. Think of a black hole not as a sink, but as a ring slowly consuming everything in its path. As it absorbs more and more matter, it becomes more powerful, pulling in even more particles and gases. This creates a swirling vortex of energy that can be seen from light years away. So what does this mean for our understanding of black holes? For one, it means that we need to shift our focus from the singularity to the space around it. By studying the patterns of particles and gases, we can gain a better understanding of how black holes operate and what they are capable of. But the implications of this theory go beyond just black holes. Holographic duality has the potential to change our understanding of the entire universe. It suggests that everything we see and experience may just be a projection of something else, a hologram of sorts. This may sound like something straight out of a sci-fi movie, but it's a real possibility. According to this theory, the 3 dimensions we perceive are actually just a projection of a 2-dimensional surface. This concept may seem mind-bending, but it's rooted in science. The holographic principle is a well-established theory in physics that suggests information in a region of space can be represented by information on the surface of that region. In other words, the information contained within a space can be projected onto its boundaries, creating a kind of hologram. If the holographic principle holds true, it could revolutionize our understanding of the universe. It could mean that everything we know about the cosmos is just a projection, a mere shadow of something else. But what could that something else be? Some scientists believe that our universe could be just one of many holographic projections, each one representing a different version of reality. This could mean that there are countless parallel universes out there, each one only slightly different from our own. And if the black holes being gateways thing comes into play, they could just be the key to understanding everything. But hey, all of these are still just theories. Things are a lot different once you actually start to understand them. These invisible giants of the cosmos have been the subject of scientific speculation for centuries, and now, thanks to the groundbreaking work of the Event Horizon Telescope (EHT) collaboration, we finally have a stunning visual of one at the center of our own Milky Way galaxy. Meet Sagittarius A*, the supermassive black hole that resides at the very heart of our galaxy. Scientists have long suspected that this enigmatic object was a black hole, given the evidence of stars orbiting around something that was invisible, compact, and immensely heavy. But the image they've captured provides the first direct visual evidence of it. The image itself is a thing of beauty, and it's hard to believe that what we're seeing is a black hole. Although we can't see the black hole itself because it's completely dark, we can see its glowing surroundings, which reveal a telltale signature, a dark central region surrounded by a bright ring-like structure. This ring is actually light bent by the powerful gravity of the black hole, which is an astonishing 4 million times more massive than our Sun. That's enough to give you a bit of perspective about the sheer size of what we're dealing with here. But how do we manage to capture such a mind-blowing image of this invisible object? Well, it wasn't easy. The black hole is located about 27,000 light-years away from Earth, which means that it appears to be about the same size as a donut on the Moon. To capture an image of it, the Event Horizon Telescope team had to create a virtual telescope that was the size of the entire planet. The Event Horizon Telescope linked together 8 existing radio observatories across the planet to form a single Earth-sized virtual telescope. They then studied Sagittarius A* on multiple nights, collecting data for many hours in a row, similar to using a long exposure time on a camera. The result is a stunning image that provides overwhelming evidence that the object at the center of our galaxy is indeed a black hole. But the image is more than just a pretty picture, it's a scientific breakthrough that has greatly improved our understanding of what happens at the center of our galaxy. The image has confirmed many predictions from Einstein's theory of general relativity, and it has given us new insights into how these giant black holes interact with their surroundings. But there's still a lot to learn about it. You see, Sagittarius A* may be the black hole that's closest to us, but it certainly wasn't the first one that we've been able to study in depth. Before we could even see Sagittarius A*, we were already studying another black hole, M87. M87, also known as Messier 87, is an elliptical galaxy located in the constellation Virgo. Its nucleus contains a black hole, which in 2019 became the first black hole ever to be directly imaged. But even before we saw its shadow, M87 was already a source of intrigue for scientists. One of the reasons that M87 is such a fascinating object is because of the powerful radio energy it emits. In fact, it is the most powerful known source of radio energy among the thousands of galactic systems constituting the Virgo cluster. This suggested the presence of very hot gas in the galaxy, which was confirmed when M87 was found to be a powerful X-ray source as well. But it's not just the energy that M87 emits that makes it unique, it's also the way it emits it. From the galactic nucleus, a luminous gaseous jet projects outward. This jet emits synchrotron radiation, a form of non-thermal radiation released by charged particles that are accelerated in magnetic fields and travel at speeds near that of light. This radiation can tell us a lot about the environment around the black hole and the processes that are happening there. In 2017, M87 made the headlines when the Event Horizon Telescope obtained images of the central region of the galaxy that showed an asymmetric ring of radio emission surrounding a dark object. That dark object was the black hole's shadow, and the image was the first direct evidence of a black hole's existence. The black hole at the center of M87 is no ordinary black hole. It's a supermassive black hole with a mass of 6.5 billion times that of the Sun. The ring of radio emission around the black hole's shadow is brighter on one side because the black hole is rotating. Material on the side of the black hole turning toward Earth has its emission boosted by the Doppler effect, making it appear brighter, and the gravitational energy released by gas spiraling down into the black hole produces a beam of electrons accelerated almost to the speed of light. The bright gaseous jet that emanates from M87 is thought to be radiation from this beam of electrons. These jets are among the brightest objects in the universe, spanning distances of up to hundreds of thousands of light-years. They are thought to play a crucial role in the evolution of galaxies by heating up and expelling gas, which can limit further star formation. The discovery of M87's black hole and its surrounding disk has provided scientists with an unprecedented opportunity to test Einstein's theory of general relativity, which predicts the behavior of gravity on a cosmic scale. That, combined with the information we've been able to learn by studying Sagittarius A*, takes everything to a whole other level. Now that we have a clear image of a black hole and information from two of them, it opens up so many doors for the world of science to learn more about them. While we can't get as close to M87 as we can to Sagittarius A*, the fact that we can actually study two of them means that we can finally compare two actual black holes. This tiny detail could literally change everything. And on that note, we'll wrap up today's video. Do you believe black holes like Sagittarius A* could be a gateway to another galaxy? Let us know in the comments below. If you liked this video, please give it a thumbs up and subscribe to our channel for more videos just like this. We'll see you in the next one.